We've been learning about different types of sequences, and we're borrowing these rules of sequences from our understanding of functions. So a linear function can be written in two ways. Explicitly, the linear function is y equals mx plus b. And that's the version that will tell you any value in the future if you just plug in an x value. The recursive model looks like y sub n equals y sub n minus 1, and then we add our m value. So we're just taking last year and we add the same number to last year over and over and over. Now, these translate into a specific type of sequence. What is a linear function called in terms of a sequence? Arithmetic. And you might ask, why do we have two different names for the same type of function? And the answer is, I don't really know. We just do. Yes. Now, quite often, when you're talking in terms of sequence, these terms get flipped around. So it would be b plus m to the x. A lot of times they write it that way, just for fun, I guess. The other function we studied was exponential. What did an exponential function look like? Y equals b times m to the x. And any time you have an x in the exponent, your variable in the exponent, and there are no other variables anywhere else, it's exponential. The recursive model was y sub n equals y sub n minus 1 multiplied by m. So if you multiply last year by a constant, it's an exponential equation. Okay? Exponential equations translate into sequences. What are they called? Geometric. Now, I don't really know why we call them arithmetic sequences, but the reason we call them geometric sequences is because a lot of times they have geometric patterns. Let me show you one. So, going back. Okay, hang on a second. We're waiting for Chaseless. You got it? Okay, good. So let's look at the geometric sequence 1/2 to the n. So this is like a bank account that starts with $1 and it's losing half of its money every year. Now the difference between sequences and functions is the difference between a solid line and a dotted line. So if your bank account was gaining money, in theory it gains a little bit at a time, but sequences skip from number to number. Okay? So this sequence would be 1/2, 1/4, 1. Wait. That's not true. It's not 1/2. It's 1. We're going to start with, we'll start with n equals 2 to show you how this works. So 1/4 plus 1/16 plus 1/64, and so on. Okay? Now, a lot of times, geometric sequences, if you add them all together, so the sequence is 1/4, 1/16, 1/64, and so on. If you add all those together, they don't equal infinity. You would think if you add an infinite number of terms together, then eventually you'd reach infinity. But in this case, it actually equals a number. Let me show you the pattern. So I'm going to draw a square. And for this square, I'm going to color in 1/4 of the square. So I'll color in all of this. Okay? And now I'm going to color in 1/16 of the square. So if I cut my fourth into 4 pieces, and I color in one of those pieces, that's 1/16. 1/64, I'll just cut this into 4 pieces and color it in. The next one. And then I just keep doing that over and over. So the question is, if I were to add up all of these colored boxes, how much of the total square would it represent? Some people think a half. Any other guesses? Third? Any other guesses? Well, it's got to be more than a fourth, right? Because this is a fourth. Okay. Any other guesses? Hang on, you're going to ruin the fun. Okay. So, well, let's look at it. Could it be half? Why not, Ren? It's obviously not 1/2. Well, it can't be all of it. One would be all of it. If I added just the colored pieces together, it cannot be a half. Well, it's got to be less than 1/2. Can you look at that and say it's obviously not 1/2? How? 2/4. Right, but how do I know it's not 2/4? Right. If that's a fourth, in order to be a half, it would have to totally fill in that other fourth. Or the other way to look at it is, that's half, right? So we know that the total number is somewhere bigger than 1/4 and smaller than 1/2. It could be a third, maybe, or some other number inside of there. So we could find out. We could add them together. So we could say 1/4 plus 1 over 4 squared plus 1 over 4 to the third and then we could add 1 over 4. Oops. So plus 1 divided by 4 to the fourth. What does it look like we're approaching? Plus 1 divided by 4 to the fifth. It looks like it's getting closer and closer to 1/3. And that is, in fact, the answer. But we can look at that picture and see it. Yeah. So let's break this into smaller pieces. Okay. Let's look at this. What do you notice there? It's a third. If I were to look at these 3 squares, then 1/3 of it is colored. Can I do that again? If I look at this, what do you notice? It's 1/3. Okay, if you look at this, 1/3. Am I ever actually going to reach 1/3? No, because there's always another box to outline. Okay? You can always just go one step further. Okay? But we can get as close to 1/3 as you want. Let's say you want to be within 100 decimal points. Well, you just got to keep making smaller and smaller squares. And that's what we mean by the answer is 1/3. We can never actually get there. But the rule says, if I tell you how close to get, can you reach that closeness? And if the answer is yes, then it does equal 1/3. If I were to say get to 1,000,000 decimal places and you say, no, I cannot be that accurate, then the answer would be no. But in this case, you can always just add more numbers. Yeah. So if you look here, 0.32, 0.332, 0.333, the further I go, the more accurate decimals I have. So eventually we'd get there. This is called an infinite series. A sequence is a list of numbers, 1/4, 1/16, 1/64. A series is when you add a sequence together. So this is a sequence. Okay? If I start adding them together, it's called a series. And if that series goes on forever, it's called an infinite series. And a lot of times, geometric series, we say the word converge on a number. This converges at 1/3. The same is not true of arithmetic. Let's say I had 1, 2, 3, 4, ... and I start adding those together. Where is that going to go? What's the answer to this problem? Well, but there are more. There's also a 5 and a 6. What's that going to equal? Infinity. Arithmetic sequences, arithmetic series, if you add them together, is always either infinity or negative infinity, because they're always going up or down. But geometric series, a lot of times they actually approach a number, which is useful in mathematics, and you'll see that later on. Okay, so let's come back to this. Did anybody notice a pattern on number 1? +2, +3, +4, +5. Is that arithmetic or geometric? Neither. It's actually quadratic, but it's neither arithmetic nor geometric. Okay? Number 2, arithmetic because the pattern is +3, +3, +3. Okay? Number 3, arithmetic. What's the pattern? +1/3, +1/3, +1/3. How do you get that? Oh, yeah, that would work. So this is 4 1/3, 4 2/3, 5, 5 1/3. That makes it really easy. Or you could just use your calculator. We could say 13/4 minus 4. Oh, sorry. 13/3 minus 4. And I get 1/3. 14/3 minus 13/3 is also a third. So we're just adding 1/3 every time. So that would be arithmetic. Number 4. How do I know number 4 is not arithmetic without doing any math at all? Negative, positive, negative, positive. Arithmetic cannot do that. So is it geometric? What's the common ratio? Times a third, times a third, or times -3, times -3, times -3. Number 5? +12, +20, +28, +36. What's the pattern? We add 8 more than we added last year, which means the second differences are constant, which means it's quadratic. So it's neither linear nor exponential. All right, number 6. Arithmetic, what's the common difference? -5, -5. Okay, I'm going to let you go ahead and finish the rest of that page. Notice the last 4 are in equation form. So you need to look at the equations and decide, does that equation represent arithmetic, geometric, or neither? And then we'll talk about it. All right, so looking at number 7, what type of sequence is number 7? Geometric. Common ratio? Times 5. Number 8? Neither. What was the pattern in 8? So +3, +5, +7, +9. Add 2 more than you added the previous year. Number 9. Number 9 is arithmetic. Common difference would be adding 8. Number 10? Neither. Why? +3, +5, +7. So that's quadratic. Okay, number 11. Okay, maybe I will. Have a seat. Yes. Hang on a second. So number 11. Why is number 11 arithmetic? It's going up by 200 every year. Now, it is in the form mx plus b, except the mx and the b have switched places. Okay, number 12. It's also arithmetic. What's the common difference? No, 16 is the initial value. 3 is the common difference. Number 13. Now, 13 is a little bit tricky, but it is geometric. The reason it's geometric is because we have the only variable is the variable in the exponent. So it is geometric. Okay, number 14, arithmetic. Okay, so now on the back side, you need to decide by looking at the equation, is it arithmetic or geometric? Sometimes they give you the recursive formula, and sometimes they give you the explicit formula. So go ahead and work on those for a while, and then we'll talk about the answers. So let's look at 15. What did you get for 15? Arithmetic, we're adding 4. 16. Hey, listen up, please. Welcome back. So, 16 is neither. It's not n to the first, and it's not something to the n, so it's actually quadratic, which would be neither. 17, arithmetic. 18, why neither? Well, if I had, hold on, listen up. If I had 1 over 2 to the n, that's the same thing as 1 over 2 to the n, and that would be geometric. But the fact that there's another n in there ruins it. So it's partially geometric, but that second n messes it up. Okay, 19, geometric. Does it matter that it's n minus 1 instead of n? No, all that does is shift the graph forward in time 1 unit, 1 year, or whatever. Number 20, geometric. Good. 21, arithmetic. 22, why neither? But wait a minute. I thought that exponential equations are n minus 1 times m. Ah, good. So in this case, if it said, if I didn't drop my marker, if it said 4 times a sub n minus 1, that would be geometric. But what's wrong with the n? It's not constant. It's multiplied by 1 and then multiplied by 2 and 3 and 4 and 5. So it's not a constant ratio. It's a changing ratio, so neither. 23. 23 is geometric. 24, arithmetic. 25. How many think arithmetic? How many think geometric? We're on 25. How many think neither? Okay, well, in order to be geometric, we have to multiply by a number. Do we have multiplying by a number? No, so it's not geometric. So, let me rewrite this. 2 over 2 plus 1/2 times a sub n minus 1. Right? 2 divided by 2 plus a sub n minus 1 divided by 2. Well, guess what? This is, right? We start with $1 and we gain 50 cents every year. So it's arithmetic. 25. So number 26, arithmetic. 27, arithmetic. 28. We've already seen this one, right? It was up here. It's neither. If instead of m it was like a 7, then it would work. But that one is geometric. Is not geometric because the ratio is not constant. Good job.